Everyone's made good progress in Lab 3. It's due tonight. If you haven't finished it off yet, good luck. Get it in before the deadline. You'll discover that labs are increasingly worth more points as we ask you to do a bit more heavy lifting. And that means it's increasingly important to get them in on time, because you'll find the points are worthwhile when you try to earn your grade at the end of the term. We'll have a quiz a week from tomorrow in section, and it covers lectures 5 through 10, so through the last lecture, the one on Turing machines and programmability and computability and things like that. So today we're going to, with sort of using using the comments about programmability from the last lecture, we're going to use that as a springboard to start our design of a computer. And this is sort of, in some sense, to me, one of the more exciting pieces of the course. A lot of what I'll talk about is, there's a lot of engineering choices you can make, and people have made many different engineering choices over the year. One isn't right and the other wrong. It's just a matter of opinion. So we're going to be talking a little bit about what the choices are to be made, and then provide you with some techniques for measuring which choices are best. And then we'll make some specific choices for this course. And so for the next the lectures before spring break and then a couple lectures after spring break, we're going to be bolting together the hardware picture for a 32-bit computer that you'll actually end up designing mostly in Lab 6. So, in the old days, we used to have buildings full of engineers that worked for years to design computers, and now it's just a lab assignment we hand out. So that's the way progress works, I think. So let's start by building a very simple computational engine. We'll slowly make it programmable so you can sort of see how that works. And then we'll back up and design a much more sophisticated programmable engine for the rest of the lecture. So here what we have is what we call a data path. And so it consists of a bunch of elements that you can sort of recognize. There's the wires are multi-bit signals. I haven't been too careful in this diagram to say exactly how wide the signals are, how many bits of information they carry. But think of them as being 16 or 32-bit buses that are carrying information around. We have a multiplier unit that can multiply two 32-bit numbers, and in this case, the implication is that we only save the bottom 32 bits of the result. As often happens in a lot of computer multiplication where you get the same width answer. We know in computing multiplications that the official answer is twice as wide as the two operands. But often in computer arithmetic, we simply take the bottom 32 bits of of multiplying two 32-bit operands together and call that the answer. And it's sort of up to you to figure out whether there's been an overflow or not in your program. Here's a unit that subtracts 1. These are two what we call load-enabled registers. You can see that in addition to a data input and a Q output and a clock input, they have a separate input called LE, which stands for load-enable. And when that signal is high, we actually load a value into the register, a new value. And when the signal is low, we load an old value. The register value doesn't change. We actually are ending up loading the register all the time. But internally, what the register looks like is this. Here's the LE signal. It controls a mux. And when LE is 1, the incoming data value is routed to the register, and then that's what gets loaded at the rising edge of the clock. When LE is 0, we actually take the output of the register and reload it with itself. So the net, even though the actual physical register is loading a new value on its D input every cycle, depending on the value of the LE register, it can preserve its value from cycle to cycle simply by loading itself with its previous value. Okay, and then we have some multiplexers which are used to choose. So this is what's inside an LE register. You can see that in this diagram, what we've done is we've added another layer of multiplexer to pick some values that will be routed into the load-enabled register. And you'll see that muxes are our friend. We're going to use muxes a lot to route values around our data path. So this is what's called a data path, because it doesn't really tell you much about what order things happen in, what the sequencing of operations is. This picture is really just telling you what's possible. And you can see that there are 4 control signals that select the value to be loaded into the B register, that determines whether the B register loads or not. And then over here we have a select signal, the A cell signal, that selects the value to be loaded into the A register and whether the A register gets loaded or not. And think of it like a little player piano, right? We're going to take a long paper roll and punch holes in it that will control whether or not at any particular moment which of these control signals are asserted. And then clock cycle by clock cycle, we'll slowly move the roll up, we'll scroll it around. And a different sequence, there'll be a sequence of control signals that gets generated, or one set of values for each clock cycle. And depending on exactly what tune we're playing, that will determine what the data path does. Okay, so what we'd like to do is to use the data path. We're going to start off with a very simple problem of using it to compute n times n minus 1, like so. And what we'll do is we want to organize the control signals so that it goes through a sequence of 4 operations. The first one consists of initializing the 2 register values. We're going to initialize A to 1 and the B register to the value n. We're then going to perform this sequence of operations. We're going to multiply A and B together and load the answer back into A, and then subtract 1 from B, and then do one more multiplication. So if you sort out how this will produce n times 1 here, which gets loaded into A. We subtract 1 from B, so that would give us n minus 1 now in B. And then we finally multiply n times n minus 1 and stick the result in A. So that's the sequence of operations. So each of these circles represents something we want to do. The arrows represent a sequence. So, and if there's no arrow between 2 operations, they can happen in any order or perhaps together. We know how to build a finite state machine to control such a thing. We're going to have a sequence of states that represents the sequence of operations we want to perform, and we'll just arrange for the output signals to be what we need them to be to do what needs to be done. So here I filled in the table. So you can see during cycle 0, the first cycle, we specify the next state of the state machine, and here you can see the state machine really is just going through 4 states, and when it gets to the 4th state, if you will, the halting state is just going to sit there and loop, doing nothing. You can see down here that none of the control signals is asserted, so no values in the data path are being changed. The register contents remain unaffected because I'm not loading the registers anymore. And so this is sort of represents the end state, but to get there we're going to go through state 0, state 1, state 2, and state 3, just in sequence. And for each of those states, we specify a particular set of values. So for example, if you look back at your data path, when the loads enable signal for A, the ALE signal, the thing that controls the mux, is 1. We're selecting the value 1 to stick into the register A, and we actually load the register A because A cell is 1. And similarly, when the load enable on B is 1, we're selecting the value n to be routed to the input of the B register. And when B cell is 0, we're selecting the value n to be routed to the B register. And then when the load enable signal for B is 1, we're going to actually load that register. And so you can sort of see how this sequence of operations is translated directly into a particular combination of control signals, which causes that set of operations, the data path, to actually execute the specified operations. It's a pretty simple recipe, pretty straightforward. Any questions about that? And I mean, we're going to start complicating it here for a second. But so think of this now as a system where, so we can basically embed this control table into one of our little FSM implementations, which consists of a ROM, which provides these output values, and a state register that provides the current state number, which is used as the address to look up what the value should be. Okay. Now we notice that some of these operations can actually be performed in parallel. The first 2 we sort of recognize could be in parallel here. This one is a little bit harder to see in parallel. If you thought of it as a programming language, clearly you want to use B before you decrement it. The idea was to actually multiply 1 times n as our first operation here, the first here in state 1, the first time through it. But if we think a little bit about the hardware works, remember that we're loading the new value into the registers at the end of the clock cycle, right? On the clock edge that separates one clock cycle from the next. And what we can see by looking at this is, in fact, we can do these two operations in parallel, knowing that A and B will change simultaneously. And this reference to B here actually refers to the value of B throughout the cycle, so this value of B and this value of B are in fact the same numeric value. They're both referring to the same sort of numeric contents, the current contents of the register. And then this assignment operator is really saying, at the end of the cycle, please update the register with these newly computed values. And so this hardware actually works fine. I don't have to think of these as sequential operations. I can do them in parallel. And I've basically adjusted my table now to have one fewer states and combine some of these operations. And one of the things that's pretty neat about data paths is that you spend some time often figuring out how to use as much of them, at the same time as possible. That makes your hardware very efficient. And in fact, if you look at the fancy data path that's inside your machine, a large percentage of it is sort of in operation all the time. So they're trying to make sure that as many operations happen in parallel as possible in order to get the computation done as quickly as possible. Okay. So now we're going to add one more element to this and allow ourselves to compute factorial, which is really a sequence of these operations where we continually subtract 1 from n, or n minus 1, then n minus 2, then n minus 3. We're going to go through that sequence. And we want to continue doing that, until the cycle at which the decrement that we're about to do is going to produce a 0. So we're going to be looking at the output of the decrementer, and as soon as the b minus 1 is 0, we want to stop. We don't want to do any more multiplications. Meanwhile, we're accumulating the product of a times b, and a is sort of the accumulator, the thing that's keeping track of the product so far. We take that intermediate accumulated value and we multiply it by the current value of the B register, which is, as I say, is being, sort of B is the value of n being decremented cycle after cycle. The thing that we've added here, in addition to the control logic generating the control signals, is the ability for the control logic to sense some state from the data path, to sense the status of the data path. I shouldn't have used the word state. Sense some status from the data path. In this case, and so that would mean that we can now make our entire machine, it can have data-dependent operations. In other words, the dependency in this particular case is we can do something different when b minus 1 is equal to 0, and we can cause the machine to stop what it's doing and start a new operation. And so this sort of combination of not only generating control signals, but listening carefully to the status of the data path allows us to perform a wide range of data-dependent computations, which is really what your computer is all about. So, and so this is a very, very simple example of control signals going to the data path and status signals coming back. So what we're going to do is to actually compute factorial. We'll redraw the control structure here, where in fact we're going to loop in state 1 as long as the z signal is 0. And if we go back and look at the other diagram, the z signal is the thing that's telling us whether b minus 1 is 0. And so when z is 1, b minus 1, the value is equal to 0. And when z is 0, b minus 1 is still some positive integer. So what we'll be doing is sort of staying in state 1, causing the data path to loop and loop and loop and loop and loop, to cycle after cycle, sending it the same control signals until finally we detect that b minus 1 is equal to 0, and then we're going to be done. And the answer we want then will be in the A register. So what I've done here is to factor in the use of the z signal in building my control ROM, which I've represented in tabular form. And in fact, the only thing the z signal controls is the choice of the next state. So when I'm in state 1, and in state 0 and in state 2, the z signal has no effect. It's only when I'm in state 1 does the value of the control signal determine what the next state is. Notice the control signals are the same. They're independent of Z. It's only the choice of the next state that differs. Everybody sort of happy with this as a machine that will actually loop through many, many, many cycles, slowly computing factorial for us? I mean, it's a fairly simple little device. And the thing that makes our device data dependent is the status signal that's coming back from the control logic. Okay, so what we've given ourselves here is a little programmable engine where we have a data path that's being controlled by this FSM, and the FSM generates a bunch of control signals each cycle that affect what the data path does. And the data path listens to some status signals to change what it will do depending on whatever the status signals are indicating is happening inside the data path. So this is sort of a little cycle of I send you control signals, you're the data path, you send me back some status signals, then I, the control logic, determine what state I'm going to go to next and change how my control signals are going to work. You say, okay, well, is this really a computer? And well, sort of not. I mean, if you think about what we wanted in terms of an abstract model for computation, we needed something that had more than just finite storage, and so in fact, 2 registers isn't going to cut the mustard. It actually can only load a couple registers and perform fixed arithmetic operations, so it's not really programmable in any way. Its program is fixed, so we're going to set about fixing, trying to remedy that. And the person who really pioneered some of these very early architectures is John von Neumann in the 40s, and he sort of described the following sort of basic architecture for a programmable, electronic computer. He started off with a central processing unit, which contains the data path that we've described. Some small number of a little bit of finite storage, some small number of registers that sort of represent the current state of the computation inside of the CPU, and then some way of manipulating the values and generating new values, which can be loaded into registers and cycle again and again and again. So that's basically, think of it as just a little finite state machine. Left to its own devices, there'd be a limit to what that machine could do. We're going to add a main memory, and think of it as having memories are organized in terms of think of it as an array of locations, and each memory location will have a certain number of bits of information in it. So we're going to send an address to the memory to tell it which location we want, and it will return to us all the bits in that particular memory word, that particular element of the memory array. Okay, and the idea is that this is, even though we have some small little finite scratch memory inside the central processing unit, conceptually this can grow quite large. And in fact, most of you own machines that if you felt rich and famous, you could go out and plug more memory into, unless you have an Apple machine, in which case they've soldered it on the board, and Steve Jobs has already figured out how much memory you get. Conceptually, we could make the memories bigger and bigger and bigger. With a 64-bit machine, we could spend a lot of money plugging in more and more memory chips if the actual electronic board. But from an architectural model, we wouldn't change much inside of here if we, to add more memory, it would we'd just have a larger capacity. We'll say more about some of the limitations of what's actually built into here in a couple of weeks. So we're going to talk more about memory systems later. Okay, so that memory is sort of our stand-in for an infinite tape. And we're going to substitute, instead of infinite, we're basically going to be able to talk about expandable storage. So conceptually, we can make as much memory as we want, although we're not quite at infinite yet. And then finally, we'll add a couple devices that will allow us to get answers into and out of the machine. So you have network interfaces and screens and keyboards and stuff like that. And so that's what makes all of the computation interesting, is that we're able to feed it values and get back answers. Okay. So how does it achieve programmability? I mean, what about the diagram I just showed you meant that you could change what it does? And what von Neumann's insight was the idea is memory is not going to only be sort of a place to put data. Okay, but it's also going to be a place to put the actual instructions that tell the machine what it should do cycle after cycle after cycle. So the machine will actually reference memory for two pieces of information. One is any data values that it needs to read and write from its local scratch memory. And the second thing is that's where all the instructions that tell it the sequence of operations. So the idea is instead of building that into the read-only memory that inside the FSM here, we're going to design an FSM here who will go out and actually get an instruction from memory, which will be bit-level encoding of the operation we want to have performed. And then we'll do that. We'll perhaps change some values in the scratch pads, or the scratch memory inside the CPU, or maybe update a memory value. And then we'll go back to memory to get the next instruction. So there'll be this notion of a current instruction. So we'll have a separate little piece of the machine whose job it is to keep track of what instruction we're on, where in memory we should get the next instruction from. And at least conceptually, we'll just increment that index of the next instruction index from, as we step through the program. And perhaps if we do loops and stuff, that index will go back and so forth and so on. Okay, so what we've built in here is really an interpreter, okay, a little hardware interpreter whose job it is to pick up a set of operations to do from memory, do them, and then continue. So in some sense, this is sort of like a universal Turing machine, right? It's referencing the tape not only for the data that the program is operating on, but for the sequence of operations that make up the program. Yes?
So for a little factorial machine,
yes.
The hardware was specifically, like you had a times and a minus?
Right, so we're going to actually build ourselves a much more interesting repertoire of instructions and hope that we can use them to do any computation that we want. And today and next time, we'll spend a little, we're going to be agonizing over whether our list is complete. Do we have everything we need? And it turns out the list is surprisingly short and sweet. And in terms of the sort of computations a machine can do, well, you actually know the answer to that, or you will by 6 a.m. tomorrow morning. You've designed the arithmetic and logic unit that we're going to be using. So it's a little repertoire of some arithmetic, some logic, some shifting, a compare instruction. That's what this machine can do, and that's in fact really what most of these machines can do. Little variations, but we'll talk more about that. Okay. So we have a single expandable memory pool for both data and instructions. So here's a slightly more sophisticated picture, or a different picture. Here we have, this is the CPU that I've broken apart into the data paths and the control unit. I like to think of those as sort of the brains and the brawn. Right? So the control unit is the thing that's supplying all the direction. It figures out what to do. And the data path is the thing that's actually in charge of manipulating the numeric values and updating scratch pad registers and things like that. And they both have connections to memory. There's a way in which we can provide addresses to memory to talk about a particular location. In the case of interacting with the data path, we can both take values, data values from the memory and put it into a scratch register, or we can take information from the scratch register and write it out to memory. So there's this sort of notion of a load and a store. And over here, the control unit's reference to memory is really just to read the memory to fetch the next instruction. So your memory is sort of divided up into holding both data and instructions. So inside the data path, we're going to have a larger repertoire of registers. We're going to actually choose to have 32 registers, each of which can hold a 32-bit value. We're going to have a way of selecting 2 of those registers to operate on. So this is a big 32-to-1 mux that is choosing which register value becomes the A operand for the ALU. And we have another 32-to-1 mux that's selecting which operand becomes the B operand to the ALU. And in fact, you can choose the same register, so you can operate on 2 copies of the same value or different registers. We have to figure out what function the ALU performs, and in fact, you already designed a unit that takes a 5-bit opcode that takes 2 operands and does something to them and produces an answer. You produce a data value that's out, and you also potentially produce some condition codes, some ZV and N bits and things like that. Okay, and then the final thing that we need to do is specify which one of these registers here will get the resulting value. So we can read two values from the registers, called a register file, okay, and then we can go ahead and select an operation, and then finally we write the answer back into a particular destination register. Very simple idea. So the scratch pad is involved in every operation. That 32 register scratch pad is involved in every operation. And then occasionally we'll move information from the scratch pad to memory or from memory to the scratch pad. In terms of the instructions, we have something called the program counter, which is that index that I talked about that told us where the instruction should come from in memory. Right? So it's an address of a particular instruction in memory, and we get back a coded representation of the operation we want to do. This encoding will tell us everything we need to do about how to set up the A cell and B cell and FM and dest operations. It will tell us what to look at in terms of the condition codes from memory. From the ALU or from the data path to figure out what the next thing we should do is. Mostly what we're going to do is compute a value, put it back into the scratch pad, and then this little loop here is a very simple idea of the control structure. We're simply going to step through memory executing instructions. And either at the end of this lecture or at the beginning of next, we'll do something a bit more sophisticated. Okay. So this is where the fun comes, right? And this is where, at various times, people have wildly different ideas about what should that encoded instruction look like. And we'll have some specific thoughts. There's this great scene in one of the old Pink Panther movies where the meanie drags the young heroine into the back room. And then all of a sudden you hear her scream, "Ah!" And so the Pink Panther runs back, all gallantry, of course. And he discovered that what the guy has done, he's lashed her to a chair and he's pulled on this big metal glove with long claws and is standing like this next to a blackboard, waiting for it to squeak. So obviously pure torture, at least to the Pink Panther's mind. Sorry about that. Okay, so. Okay, so what is it we need to specify, right? Well, there's this sort of notion of we want to be able to specify, ooh, I can see my claw marks right there. We want to specify an operation, and the operation almost certainly needs some operands. And usually there's a destination involved or where to put the result. And so we would expect whatever we're going to do to involve some way of taking our instruction word, our binary encoding of the instruction, and have it specify everything that we need to do in order to make our little data path do its thing. And some data paths are complicated. They have lots of places to get information from in terms of operands. Some only fetch information from the scratch pad registers. Other instruction sets allow you to take one of the operands from memory. So you could, it involves actually loading some information from memory, which means you have to compute an address. People have been all over the map depending on how complicated things are. How the instructions are encoded can be quite different. Some people use a Huffman-like code, where they actually have a string of bytes, and it's a variable length code, which means that some instructions are encoded in a single byte, and other instructions take 8 or 9 bytes to encode. A simpler approach, which is the one we're going to be taking, is we're going to have all the instructions be exactly 32 bits long, and we'll choose to have just, I think, as it turns out, just 2 formats of instructions, and as you'll see that evolve in just a second. Okay. The question is, how do we decide what's right and what's wrong? And there's no right answer to that question, or no correct answer. But what we're going to do is a sort of a mix of sort of engineering tuition. What operations do you think we need our machine to be able to do? And then a little bit of sort of art and polling, if you want to think of it that way, where we're going to be running a lot of benchmarks to figure out whether the proposed feature we want to add to our instruction set actually accomplishes anything. Or, are programs run faster? Are they shorter? Or what would be the advantage of adding those extra transistors to our CPU design? Will we get something for it? Will the investment have the right amount of return? And what people have gone to, and I'll put my cursor here on top of this RISC philosophy, reduced instruction set computer. For a long time, computers got more and more complicated. and a really complicated instruction set that provided for a huge a repertoire of where you can get information from to operate, and lots of destinations and a zillion operations, not just simple add and subtract, but polynomial evaluate and FFT and so forth. How far do you go? And for many decades, the answer was, well, the sky's the limit. More complicated was better. That showed you had a more sophisticated computer. And then when we got into the integrated circuit era, in which there was a real value to things being compact and ultimately not very power hungry, we got into this sort of mode of saying, well, what's sort of a minimum set of things we can do? And in fact, if I have a simple instruction set, maybe I can actually build a machine where the clock rate is much faster. That's, instead of stuck at 100,000 operations a second, it might be able to do 1 billion simple operations per second. And it might be able to do 1,000 small operations in the same time it took you to do one complicated one, might turn out to be a better way of thinking about the problem. And in fact, that sort of turned out to be the case. So for a long time, the core execution engine inside the laptops is very much one of these RISC computers, reduced instruction set computers. And then, at least in the case of Intel processors, there's a sort of this separate front end that takes the more complicated encoding of the x86 instruction set and translates that into a sequence of these RISC operations. So we're going to build a RISC computer. And it actually, you'll discover it performs pretty well. Okay, so let me talk about, we're going to spend now the rest of this lecture and the next lecture on, or the next couple lectures on the programming model. So what we want to do is to think about, is the architecture, the machine, the instruction set that we're designing, how can we use it to do everything that we want to do? And then just after we come back from spring break, we'll actually spend just a lecture. It's actually a RISC machine is actually a very simple hardware design. We'll actually draw the schematic for the hardware interpreter for our instruction set. But we want to spend a little while making sure that we can do everything we need to do. And so that's going to take a little work. So the programming model starts off with, where does everything live? All the data and instructions in main memory. So main memory, as I say, is this big array. We're going to allow ourselves memory that can hold 2 to the 32 bytes of information. A byte is an 8-bit value. That's the name for an 8-bit value. We're actually going to organize the memory as words. So we're going to have a memory that's actually 2 to the 30th words. And each word has 4 bytes of information in it. And although most modern computers have a way of actually reading and writing a single byte from memory, our machine is going to be pretty dumb. It is just going to read and write 32-bit words. It's not going to have any byte-level operations, which might be a deficiency, might not. You can certainly write sequences of 32-bit operations that let you pick up a whole word and shift it and mask it to get just the byte you want. And that might turn out to be a good thing. We'll see. We'll see how it evolves here. So we have this sort of memory organized as 32-bit words. And conceptually, when we send an address to the memory, we're going to be asking for a whole 32-bit value to come back. And the address that we always send always has the bottom is a 32-bit address. So it's going to be a 32-bit address, which is the 30-bit word index, and the bottom 2 bits will always be 0. And you can say, why are we doing this, Chris? This seems very complicated. Couldn't we just do a word address memory? Well, this is all sort of lost in the mist of history. We're trying hard to be compatible with machines that you're likely to see, which almost all support some level of byte addressing. So we've adopted byte addressing as our convention, but we're going to only use it to address words. So the bottom 2 bits of the address will always be 0. Okay. In terms of what's inside our CPU, our combination of data path and control logic, we're going to have those 32 registers, 32-bit registers. Now each one of the 32 registers holds a 32-bit value. So you can see this 32-bit data path, which is what you guys have built, is sort of going to be the 32-bit word is our basic building block. One of the registers will always read as 0. Register 31 will always read as 0. So that means that if you specify register 31 is one of the possible operands, what gets supplied to the ALU unit is a 0 value. If you specify it as a destination, that's like throwing the value away because you can't change the contents of R31. So if you're computing something and you really just want to look at one of the condition codes or something like that out of the ALU, but you don't actually want the result of the arithmetic computation, you can specify a destination of R31, which causes the value to be, it doesn't change anything, the user visible state, the program state. So an attempt to write into R31 has no visible effect on the state of the machine. And then finally we have the program counter, which is the thing that's going to be incrementing and showing us where the next instruction comes from. So the fetch and execute loop is we're going to go off and fetch that 32-bit encoded instruction, and I'll show you what the encoding looks like in just a second. We're going to increment the program counter, and remember, because we're stuck in this byte addressing hell, we're going to be, when I say increment, we're going to go to the next word of memory, which means we're going to increment the byte address by 4. That moves us 4 bytes farther along in memory, or one whole word. We execute we look at the encoding of the instruction that we fetch. It's actually a 32-bit value that's come back from memory. We look at those bits, and that will tell us what to do, and I'll show you how in just a second. And then we just repeat. And if you do the design project, you'll probably be able to design a piece of hardware that can run, do one of those operations every 5 or 6 nanoseconds, which will be pretty good. Yes?
So the processor has 32 registers.
Yes.
Each of which can hold 1 word.
Yes.
Each word has 4 bytes.
Well, so I'm with you up to there, and what you said is exactly true. But for most of our purposes, you just forget about bytes. We'll not spend a lot of time talking about bytes.
Each word is 32 bits.
Each word is 32 bits. The values are treated like 32-bit values. You manipulate them as 32 bits at a time, and we go from there. Okay, so here are our 2 instruction formats. And you can see that we have 2 possibilities. We have something where we can specify an opcode, a 6-bit opcode. So what we're going to allow ourselves is 6 bits here. How many different combinations of 6 bits are there? So our machine can have 64, which is equal to 2 to the 6 operations. Okay. The operands we're going to set aside, we're going to use 5-bit fields. How many different things can I specify in a 5-bit field? 32 things. So that can allow us to name each of the 32 registers. So in this particular format, the reason that we put little r's here is to remind us that we're actually putting in register addresses. Those are 5-bit numbers, 5-bit 0, 1, 0, 0, 0, or something like that. 5-bit values that actually are the index of the register that we want to access. So we can in this particular format of instruction, we can specify the operands as each coming from 2 registers, okay, and the result will be stuck back into a RC register. Is that a question in the back or just a nice stretch? No, it's fine. Stretches are good. Okay, and then the second format, the second operand, instead of coming from a register, is actually a 16-bit constant. So it's very simple, right? We can do one of 64 operations. The destination of each operation is always a register. What happens if we don't want to store something? We specify a destination of 31, the binary value for 31, which is R31, which never changes even if we try to write in it. If we want one of our operands to be 0, we can specify R31, and that will always supply a 0 value as the appropriate operand. Everybody sort of see how that works? It's very simple encoding. And that's why this is a reduced instruction set computer. There's no complication to this at all. We'll be able to, when we build the hardware, we're going to use most of the bits of the instruction directly as signals in our electronics to actually control, the address of the little register memory, and which value we're going to be reading out, the destination address. And then we'll just have a little ROM that will help us decode the opcode bits into the appropriate control signals for all the different things that, ALUFN and all the other things we'll want in our data path. Okay, so those are the basic instruction formats. And now I'm going to spend a few minutes and I'm going to go through and I'm going to cover, 90% of the instruction set of the machine in 2 slides, right? And the thing is that, and this should be completely understandable because these are the instructions that basically let us operate, use the arithmetic and logic unit, the ALU that you designed in Lab 3. Right? So we have, here's a list of all the operations that your ALU can do. You probably didn't do division. You didn't implement division. You weren't asked to implement division. Many of you looked at least at the problem of implementing the multiply. But at the software level, we're designing an instruction set that has all of these arithmetic operations. In a couple of weeks, we'll talk about what happens. You know, maybe we can use software to fake any missing instructions in the hardware. And in fact, we'll show you how that could work in our machine. So it's not clear that every machine needs to implement every possible instruction, but we have to implement enough instructions that we can fake the instructions in software for any operations that we choose not to implement in hardware. So here's a set of operations: the compare instructions, the Boolean instructions, the shift instructions, and the arithmetic instructions. And all of these can be implemented by your ALU, with, as I say, with the exception of divide. And the way this works is that we're going to encode the two register operands, where we want to read the values from. Okay, and so if we want to read from R2 and R3, you can see that this is the format of this instruction here is sorry, if I want to read from R1 and R2. So the order of the operands here in our symbolic representation of a single instruction is RA and RB and RC. So R1 and R2 are the two registers we want to read. And you can see we've encoded 00001 as the encoding for the register 1 in the RA field, and the register, the numeric value, binary value for 2 in the RB field. So that's specified. Please read register 0 for the A operand, or register 1 for the A operand, and register 2 for the B operand. And when you, this is the operation I want you to perform. I've encoded add using this particular combination of the 6 bits, and put the answer back into register 3. Right, so suppose I wanted to do the instruction. I'm just going to write up something else here. So suppose I wanted to say multiply R3 times R5 and put the answer into R17. Any conceptual problems with how you could take this sort of symbolic representation of an instruction I wanted to execute and encode it using those bits? Right? You know what to do with these three values, right? These go into the RA, RB, and RC fields. So you need to turn each of these register numbers, 3, 5, and 17, into 5-bit binary values and just write those little 5-bit strings in the right place in the instruction. What else do you need to know to complete the encoding? I would need to know what the 6-bit opcode was for multiplication. And when we actually get to the hardware, I will hand you a sheet of paper that tells you all the encodings for the opcodes. Okay, so all pretty straightforward. Alrighty, so now we have, you know, the next 40%, 45% of the instruction set, which is the also ALU operations. What's the difference between the instructions on this page and the instructions on the previous page? Well, the answer is that the difference is that, first of all, that different opcodes. So this is another set of opcodes, another set of whatever it is, 16 opcodes. This uses the second format of instruction. So there's a bit here in our opcode encoding that tells us we want to use a different format of the instruction, which means the second operand is actually encoded as a 16-bit constant in the instruction itself. So instead of the second operand being from a register, is actually a 16-bit number that is part of the instruction. Now we need a 32-bit operand. What do I need to do to convert a 16-bit number into a 32-bit operand? I need to sign extend it. And you'll talk about that in recitation, right? It actually doesn't involve any hardware, but you do have to make 16 copies of the higher order bit of this numeric constant here, of this bit here, in order to convert a 16-bit representation of an integer into the equivalent 32-bit representation of the integer, which is actually what gets fed to your 32-bit data path. And we use this C here to add constant to sort of remind ourselves that it's somehow different from the operations on the previous page. So you say to yourself, well, do I really need that? Couldn't I put all the constants in memory and just sort of, I haven't shown you load and store yet, but I will in a second. Couldn't I just load them into a register and use them there? What's the advantage of encoding constants in the instruction? Does that actually bias anything? Will my program be shorter? You know, will it run quicker because I don't have a memory access to get that second operand? You know, is there some advantage to doing that? And now we get into the sort of technique that I was talking about before. You know, the political people call it polling. We call it benchmarking, where what we do is we pick some programs and whose performance we feel is representative of the type of programs people will be running our machine. In this case, this particular set of benchmarks, which is from Hennessy and Patterson, famous architecture textbook. The Tech word processor, SPICE is a circuit level, like JSON, circuit analysis program. GCC is the GNU C compiler. And what they did is they basically tried, they built a compiler that knew about these instructions with constants, and then they went off and said, well, how often do I use this feature? Is this like a feature I use all the time? And the answer is, oh, it turns out almost all the comparisons that are in most C programs are comparisons to these small constants. Almost always when you say, well, you can see, 80% of the comparisons are actually against some small number, 3, 17, something that fits into a small integer value. Okay, over about half the arithmetic operations, one of the operands is a small number. We'll talk about loads and stores in a second. So you can see here that in fact, almost all the time, making a provision for arithmetic operands, for integer constants as one of the two arithmetic operands, is really quite useful. So this feature appears in almost every instruction set, the ability to encode constants as part of the instructions directly. Okay, so here we have our first little program. We're going to take the contents of R1, subtract 1 from it, and put it into R2, and then we're going to take R2 times R1, so if R1 contained n, so R2 now contains n minus 1, so we're going to take R2 times R1, so that's n times n minus 1, put the result in R2. So these are two separate 32-bit words that would live in memory that would encode the operation we would like to do. Now I'm going to add one more feature here just before we end the lecture. We have 3 or 4 more minutes, and I'm going to use them to talk about loading and storing information from memory. So we have a load operation and a store operation, and they both use the second format of instruction. So the two operands to the ALU will be the contents of a register and this 16-bit constant. Those are used with a plus operation. We're going to have the ALU do a plus for us. Those two values, these two 32-bit values, are added together to form the memory index, the memory address that we send to memory. We get back the value from memory, and that simply gets put into a register. So the load thing is computing an address by adding a register and a constant. So we have different ways of, depending on what that register value we choose and what constant value we choose, we have a way of computing the address of the location that we want. We can send that to the memory, a data value comes back, and we take that and we stick it into the RC register, whatever register we specify. And store does exactly the same address computation, but instead takes the value of the RC register and sends it to that memory location. So load and store are sort of symmetrically opposite. So now we have a way of moving information to and from our scratch pad. Everybody, so the arithmetic operations, with or without an integer constant, is the second operand, and then load and store. So this is what we call a load-store architecture, because the only way we can reference memory at all is either we can load a value from it or we can store a value into it, but there's no other instructions that reference memory. Okay, reference memory as data. All we can do with memory is load and store. So the way we do our storage conventions is that when we have variables in our C program, here's x and y, we just allocate 32-bit words for them. So if we have a little program that has variables n, r, x, and y in it, what we do is allocate specific memory locations. And here you can see x was stuck in the memory location whose address was hex 1008. These are all hex numbers here. And so we use a load instruction to compute that address. We actually are adding 0, that's the contents of R31, to this constant. So this is really a constant memory address. And going out to memory, getting the contents of location 1008 hex and sticking it into R0, doing some multiplications, in this case by a small integer number, and storing the result back as the value of y. Okay, and sometimes instead of building in numeric constants, we use this sort of symbolic representation for memory addresses. We'll talk more about storage conventions next time. Now, you can say, well, computing memory addresses, there must be 1,000 ways of doing that. I mean, and in fact, this is a set of the memory address operations that are available on an old-style machine from the 80s. They got quite complicated. They were all set to, in a single instruction, be able to index into Fortran arrays of integers or reals or doubles or things like that. And you sort of go, well, these are all very complicated. The beta can do the ones, the instruction set that we just designed can do one of these three. It actually does displacement all the time. But if you specify R31, that's like absolute. And if you specify a constant of 0, that's like indirect here. So this is what we can do. Do we actually need all of this? I know. What does the audience say? And so we do our benchmarking, and we can see all these complicated modes, although they seem very appealing to us, turn out to be not very useful when it comes to, most programs don't use them very often. So instead of putting in a lot of extra hardware, we choose to leave it out and say we might have to fake it with a couple of instructions in a row, but we do it so rarely that the program will hardly be any bigger or take any longer to execute. Okay, so I'm going to stop there, and we'll pick it up again next time. And meanwhile, good luck in finishing off Lab 3, and we'll see you next week where we're going to work more instructions. Just a few more.